So people talk of a time when all forces were unified like they aren't already. Um, they all function on the same principles but at different scales. Uh, I think this is kind of an important thing to think about, and I'm not sure if I actually have a talk that really goes into this one thing I wanted to talk about. So I'm going to mention it in this one. Um, where did I write that then? Oh, maybe. Okay, I do have some other ones. I didn't realize there was more. Okay, never mind. um. What was I just saying? Um. Sorry. They all function on the same principles, but at different scales. The universe expanded so quickly in our perspective because we experienced less gravity. The gravity of the universe would have been much greater at the beginning, and so time would have moved slower than it does now. As such, the expansion speed does not break the speed of causality. Um, that seems like a kind of separate point, but that is actually part of what I wanted to mention. But I guess this is going to be that talk then, actually. So never mind. So pretty much what I'm trying to say here is initially what I'm trying to say here is that we have the four fundamental forces, right? We have gravity, the weak force, strong force, and electromagnetism. But we only can fit three of them into quantum mechanics. And we're like, gravity is not quantum. What's going on? And really, what I want to kind of say is that none of it's really that quantum. I'm not a huge fan of the thinking that everything's in this field and it's all just excitations of a field and it's all waves. I'm not convinced on that. I do think that quantum mechanics is very effective in predicting our universe, but I don't think that means it's necessarily right on why. I think the calculations and the math works, but the reasoning behind it is not necessarily correct. But moving on from that, right, we have gravity, and I think that basically we have mass exists, and mass is energy. Mass creates energy through gravity by pulling in dark energy, which dark energy is the fluid that's basically all around us. It's everything. It fills all the void and the empty space between atoms and stuff is dark energy, and so this dark energy is being sucked in, and we see this as curvature in space-time or gravity. And what's really happening here is that the dark energy is flowing into mass. We see this flow as the flow of time, and this dark energy is then converted into, energy that is into mass. And this conversion is done by basically taking virtual particles as they form in the vacuum, or vacuum energy, taking these virtual particles, and what mass is doing is basically debalancing the virtual particle pairs to create, and is taking a portion of the energy that is there, right? As this virtual particle is created, it snatches one of it, it debalances it, or snatches basically one of those virtual particles. It'll put energy into the virtual particle pair. The virtual particle pair will then collide again, and then what's left over, the bit of mass, the particle, whatever it may be. Maybe it's a photon, maybe it's smaller, maybe it's larger. I think basically what's going on in proton, we'll go deep again. In protons, basically, is they're powerhouses of this process. But, you go into a proton, you go into the quarks. I think that what's going on in a quark is you got these gluons flying around. These gluons flying around are either transferring energy, or basically they've got kind of they're almost like a net of like sending energy out and seeing if they get a collision. When they do get collisions, that creates energy. That energy is then taken in, and then excess energy is taken in. It's used to create new quarks if needed. If it's not needed, okay, we'll get rid of the old quarks, make new quarks again, and some of that energy is lost in that process. That goes out. Electrons say, I'll take that, and they take a piece, and so on and so forth. And so basically what I'm trying to say here is that I really got sidetracked there. Gravity is caused by this consumption of dark energy. Dark energy being consumed, again, it creates gravity. And then when mass spits out that excess part, like I said, we don't need this bit of energy, send that out. Or when matter is just sending out these particles to try and, create more energy. It sends this energy out. These photons it's sending out are being sent out with the potential to interact with these virtual particles, and when they do, they collect that bit of energy from that interaction, and then when they interact with something else, then that thing takes in that excess energy, and so on and so forth. But what's happening is that the radiation of these particles, we call them, it's not even necessarily photons as what we call photons, but it's the like virtual particles of quantum mechanics, these virtual particles that are created to create these interactions, to create these positive and negative charges, and attractive and repulsive forces, or these virtual particles. These virtual particles are not virtual, they're real. They are just so tiny we can't really see them. We know something's happening, so we call it virtual particles. We just don't know what it is. I think these virtual particles are real. There are photons, basically, that are on a smaller scale than what a photon is that we believe, because I think photons are actually a collection of these actual photons. A photon is more of like a clump of photons than actually a photon. But that's beyond what I'm talking about right now. So sending out these photons to collect more energy, basically, and release excess energy, or whatever is the electromagnetic force. And this electromagnetic force is also the same thing that is the strong force. It's just on a smaller scale inside of these like protons and neutrons. And so we know what's going on there is basically charges, and passing of gluons back and forth. I think that it's also this electromagnetic force just on a smaller scale, and it's less the radiating excess, which is what electromagnetism is. It is the actual passing of, or the actual collection process at play here. So, it seems different, but it's actually the same thing. It's the same process, but it's just, a different part of it. And then the electroweak force is just the balancing of the equation. It's like, we have excess energy here, let's send that off. If I've talked about this already, but if there's not enough energy in the system to sustain itself, then it's gonna cut energy off so that it can find balance again. So the electroweak force is part of this radiating process to get rid of excess energy. And it's not necessarily this whole force on its own. I think all of these fundamental forces are like us looking at the process of a cell right, and calling the different processes of a cell to create, energy as we see it, like ATP, right? We don't look at a we don't look at a cell in our body and say, oh, the process of creating ATP is, the strong force, and then the sending out of, the sugars is, the weak force or electromagnetism. Like we don't say stuff like that, but I think it's basically the same thing. And I got totally sidetracked on this one. My camera's gonna die, so I will pick up in a second. All right, getting back to what I was saying. Basically, I think the main fallacy here is calling these things the fundamental forces and making it seem like they are completely separate from each other. And there is talk of the electroweak, like the electroweak force, and basically how we can see how they combine together, and we believe that, we could get all the forces back together again. Maybe at some point they were all one, and we're trying to figure out how that happened and when that happened. And I think that's kind of like a misconception there. It's like, guys, they still are all one thing. Like, I think you've got it wrong here. And looking back in time, we're looking back in time, and I think the problem we're running into here is we're trying to compare apples to oranges. Because when you look back at our evolution of like life on the planet, you look back at the evolution of life on the planet, it goes from multicellular, right? It goes from multicellular, like land animals, there's plants, multicellular life, going back down to, there's the fish that were in the ocean, and then we go towards, I'm doing a terrible job of explaining de-evolution here. I don't know. Basically, there's multicellular life now, right? And this is the time that we live in. So we're looking at everything and saying, wow, like everything's so complex. And then we look back and we see that we evolved from single cell organisms. And potentially, at some point there was no cells, right? And there was like just proteins or molecules, and somehow they came together and created life, right? And so we come from single cell organisms, a single cell, and the processes that a single cell organism uses, we still have, right? We still have those processes, but we also do more, right? And I think the problem we're kind of looking at here is saying like, wow, all these fundamental forces, look at this. And they're all part of the same process, but when we look back in time, it seems like they should all converge because they all are part of the same process. And they're not actually separate things. They're all part of one system. And pretty much what I'm getting at here is that, again, as I've said, I don't think that mass and matter is as dead as you think it is. And I don't think it's wrong to look at it as this living organism because, we see ourselves as we evolved in complexity from single cell organisms to multicellular organisms, right? And I think we're trying to look back, and what we're not factoring in is that there was an evolution process of matter as well. Matter didn't just start like this, right? It didn't just form like this, right? It's not like, and then they were finally able to, like, once the heat died down enough, they were finally able to do these things. It had, like, matter had to evolve to be capable of these processes. And it took a lot of time. But when we look back at time, getting back into more of what I wanted to speak about here is when we look back at time, we're like, oh, all of this happened in the first, picosecond or whatever, like crazy little amount of time, like in the first 3 seconds, like so much happened, right? And I think that this is also a wrong way of looking at things, because what would have been 3 seconds now was potentially billions of years. Because think about how much matter there is in the universe, and it was all in one spot. Think about if time's moving at this speed now, imagine how, it would have been moving crazy slow. I feel like this is a hard thing to describe, because like it would have been moving crazy slow in comparison, because in that 3 seconds, like I said, could have been billions of years. So to them, time was moving extremely slow. But to us, a billion years and 3 seconds, that was fast, right? So I feel like it's kind of like hard to explain that in a way that doesn't seem counterintuitive. But to us, we see, we're looking back, in 1 year, we're measuring, in 1 year, looking back 1 year to it doesn't compare well. In 1 year, it would have been trillions of years that would have passed in that 1 year, because of the difference in gravity. And I think this is another thing that's important to kind of factor in, is that we're looking back at our universe and it gets hard for us to know what the heck is going on. And I think we kind of have, we don't look at the universe as this evolving thing, but, we look back and the universe is continually expanding, and it has high energy, right? So much heat, and it's just continually expanding out, right? And what does heat do? What does light do? It radiates out continuously. It continually radiates out. It goes from a point of high energy, and as it gets farther and farther away, the energy is less and less, because not necessarily because the light itself, the photon itself, has lost energy, but the density of it, the energy density, has decreased. And so what is entropy? It's just, we're just spreading out the energy. The density of energy is reducing. So why is the universe expanding? Because everything does that. It shouldn't be this weird thing that the universe expands, because it's just stretching out. It's just expanding out its energy. Everything we witness is doing the same thing, right? Like all photons emitted are going out in every direction, spreading out, right? I think that potentially we're looking back in time and we think of everything as this consecutive universe. It happened all like that, but it happened like that, but it was a lot longer than you think. And there's I have to look at like a photo, but there's different phases of expansion where it's like, from this time to this time, it was this thick, or it was like this expanded, and then at this point, it expanded rapidly, and then it was this thick, and then expanding, and now it's expanding again. What if these points of great expansion are basically new phases of the universe, right? Because I've talked about how, like, we know how entropy is the equaling out of energy across everything, right? And so we know that as energy is like balanced out, once everything's at a point of no energy can be used, I talked about, dark energy and dark matter. Eventually the dark matter is going to use our matter as dark energy and, fuel itself and continue on, but that at that point the energy is too low of a state for us to even notice it, but a whole nother layer of the universe is still continuing to expand out. And so what if each time the universe seems to expand rapidly, what's happening is just a shift from one energy level to the next, and we're kind of like I don't know, like a photon jump, or like an electron jumping down to the energy levels, and as it jumps down the energy levels, it's emitting, it jumps down from the highest energy level, it goes boom, and it sends off a photon, right? And it sends off like a high energy photon, and then it bumps down another one, and it's quantum, right? So the difference in energy decreases each time, but the amount of energy that's there is a lot, so it keeps bumping down, and then sends off a different photon, right? And then it bumps down another energy level, sends off a different photon, right? And what if that's basically what our universe is doing? It's just the time scale is insane, right? I mean, looking at it from that perspective, it's absolutely insane. Like, our entire universe could just be like an electron or something, like emitting its virtual photons. Like, it's so, when you start thinking about it on this scale, like, it's it's like, what the heck even are we? Like, are we anything? I don't know. It's so crazy. Um, I feel like I've been rambling without actually saying. But this rapid expansion, I've heard this a couple times now. I wanted to say this, that the universe expanded faster than the speed of causality, or speed of light. But it's okay because space doesn't get bound by the same rules. And I disagree. I don't think that makes sense. It's space time. It should follow the same rules of expansion, but I don't think it actually needed to expand at all. Space doesn't need to expand. The space is there. That's what space is. We don't need to expand into the space. Or like, the space doesn't need to expand for us to move into it. It's already there. We're just moving into that space. But yeah. So yeah, basically, I think it's important to kind of realize that time would have moved a lot. Time doesn't move the same as it did then as it does now. So, 3 seconds would have been. It's not that it could have been. It would have been an insanely long time before anything actually happened, which is just kind of putting everything else into perspective, because, we don't know where we are on this scale of time, on this, whole thing, but like, we think of ourselves as, wow, there's so much empty space, right? And, what we think is like a ball this big is this big, right? We're not even close to, like what expansion is. But the funny thing about it is that expansion never ends. There's no point at which you can't keep expanding. Which, I don't know, is a whole nother thing. But there's basically, what I'm trying to get is like, every universal cycle probably results in another burst of expansion. As the energy of the system is reduced, it expands. Like the sun will, once at some point the sun's like running out of, will turn into a giant, like a red giant or something along those lines, and it's going to expand out, and they say that it's going to like be so big that it's going to basically swallow the earth up, something like that, something along those lines. And I think that's interesting to kind of think about, because it's going to have less energy but expand outward. That's kind of what we're doing, right? But Um, uh, every the system, as as the energy of the system is reduced, it expands like the sun um, will in however many years. This may be why the rate seems to change and why we see a singularity. But you know, we look back towards the beginning, you know, of the universe, we see a singularity. But that singularity is probably not actually a singularity. It's just, well, it either is a singularity or it's just at a point where it's too small for us to look farther. So to us, it seems infinitesimally small. But if you imagine a cone, right, at this, like the point here, like if it's a really thin cone and you're all the way back here, when you look back, you won't actually see the end of the cone if it's like a really thin and long cone. At some point you just see darkness. You can't see farther because the light doesn't go far enough back in this really long, thin cone. But it still has more to go, right? And so I think that may be what the kind of singularity that we see is. But it also could be that on the other side of that singularity, it is a singularity, and on the other side is a black hole that's sucking stuff in, which I wouldn't be surprised if that's the case. Um, you know, and it's just a small. This is why it may seem that the rate seems to change and why we see singularity, but it's actually just too small of a scale for us to see. We are on the other side of a black hole moving towards the opposite of what a black hole is, equal expansion everywhere compared to everything everywhere. So a black hole is everything in one point, right? And then a white hole is the opposite. It sends just everything out rather than sucking stuff in. So if we were in a black hole, right, we would, the opposite of that, to head outwards, as entropy tends to do, right? It goes away from this extremely unlikely point towards a more probable outcome, which would be expansion everywhere. And so it would make sense that a point of that condenses down to everything would then turn into a point that expands into everything. Um, and so that's why I'm basically saying, like, I wouldn't be surprised if a black hole is where we originate from, but that black hole is then in a universe of its own, and like I said, it's just kind of cycles of creation, and that goes into a whole nother rabbit hole of what the heck is going on and what are we and where are we and does it even matter. And so um, and so we are flying out into space time, and the energy is spreading out like a wave of light would, slowly reducing the amount of energy but seemingly never running out of room to expand to. And so energy levels to reduce to. So, yeah. In summary, our universe is expanding because that's just the natural course of entropy, and it's trying to spread everything out equally, right? But there's other processes at play in the meantime, and this may not have been the first time, and we may be able to see back towards times before. We just don't realize that we're looking, past what our universe is. And that's why things start to get fuzzy and we don't understand and things start to fall apart, is because the systems that we're trying to base everything off of don't exist yet. When we look back that far, multicellular life does not exist at the beginning of evolution. So, when you try and look back for multicellular life, when all that existed was single cell organisms, it starts to get very confusing. You're like, where are they all at? They should be here. But that's not necessarily how it works. So You know, we evolved, uh, particles evolved, and everything is following this path of entropy towards a balancing point, and we're something, and we come from seemingly nothing. But, you know, if there's nothing, then there's something there. So, you know, why not? I guess. Um, yeah, I don't know. Everything kind of exists because it does, I guess. I mean, I don't think you can really. I don't know if we'll ever get a better. I don't know if we're ever going to get a better answer than that. Um, so enjoy life. Peace out.